Hi, welcome to Analyzer Shorts, the series where we show you bits and pieces of AnalyzerPro, the software for traffic accident analysis that should inspire you in your daily work as an expert. Today we are discussing the topic of rear end collision slash the topic of whiplash syndrome. Depending on the legal system you're working in, these can be quite frequent topics at court, and we want to see how we can use Analyzer's serial collision module to deal with these types of accidents. We're going to present that with the example of a crash test done by the Dynamic Test Center Switzerland. Thank you very much here for the opportunity and for giving us the data. So what we have here is on the right hand side in blue a Skoda Fabia, and on the left side a Mercedes Vito. And the Mercedes Vito is not braking while the Skoda Fabia is fully braking. We have information about the braking decelerations here, and we won't look too much into the results. We will look a little bit into the damages. We can see here that this is a bit moved up. That means there has been some force pushing backwards, obviously. We can see some parts here in the back a bit destroyed. And for the Vito, we can see here a few metal parts bent in. Yeah. And we want to check how we can deal with that now with Analyzer. So I'm opening Analyzer. I have prepared a few DXF of the vehicles. So essentially what we are having is a situation like this, where the two cars are bumping into each other. This front part was a bit pressed up, and this rear part, very rigid metal part, was a bit bent in. So something like that. I'm opening now the module serial collision, and don't be overwhelmed by the huge input window. This is theoretically designed to make rear end collisions or serial collisions with up to 8 vehicles. Right now we only need 2 of them, so we will exclusively deal with this first column. So the first thing we have to discuss or decide is we have deceleration before and after impact. And so in this case we know that the rear one was braking with 7.1. In other situations we have to make estimations, of course, depending on the surface, on the braking behavior, etc. The front one wasn't braking at all, but we still have to give him some deceleration, like it's written the gear is in, and like, yeah, so some minimal deceleration, probably 0.5 or something like that, we should put in. Second, we have 2 values here, and out of these 2 values we need to put in 1. The other one will be calculated. So we have difference in velocity after the impact, or the final distance. Usually we don't know the final distance because cars might be moved away, or we just don't know it. So but the good thing is that the velocity difference after the impact is usually in an area from like 4 to 5 kilometers per hour. So we are like pretty much on the safe side if we put in the 5 kilometers per hour here. Okay, then what we have here is 3 values: ES value, energy equivalent speed, deformation after collision, and stiffness. So these 3 types of values for 2 cars sum up in 6 values. These 6 values, from these 6 values, we need to put in 3. Yeah, and they must be distributed between the 2. So I can't put in just like 3 of one car and the others not. So for those of you who are not familiar with ES, ES is stands for energy equivalent speed and is a theoretical value that in the unit of speeds that should quantify the energy that went into deformation by its speed value, since kinetic energy is mass times velocity squared divided by 2, and and it somehow like got established in accident research that people are using this value to show the deformation or to quantify a deformation. When it was designed as a control value. And what then happened is that people are using it more and more as an input value, which I personally do not recommend, since, as I just said, it's energy equals mass times velocity squared, and this is the velocity value. So the squared is the problem here. If we put in a squared value, then each error we make comes in with a square. So we should rather use the ES value as a control value and not as an input value. Deformation after collision. So what's meant by that? It's meant that when the collision happens, cars will get pressed together. And then shortly, and when the cars separate from each other, some things might pop out. Let's say, for example, plastic parts. They pop out, but they don't apply any force on the other vehicle anymore, because it's probably already gone. So what we are interested here is the real deformation, not some plastic parts that might pop out later. And in order to find it out, you should, when you examine the car, you should check out damages that lie beneath the obvious damages. So what we could do here is, I made up my mind a little bit about that before on the damages. But here, in order to get this part here, I'd say I would give him roughly 15 centimeters, and the front one is a bit stiffer here, so I give him 12 centimeters. So we have 2 values, we need a third one, and that one is probably stiffness. This is an average stiffness in that area. It's also a value we need to usually make an educated guess on, but at least it goes in not with a square as the ES value, but only linear, and typical values are between 600 and 1100 kilonewton per meter. So since the Skoda is not super deeply intruded, then I would rather be at the lower hand, so I'm giving him 700 kilonewton per meter. And then we have 2 more values for 2 cars, so 4 more values. Out of these 4 values, we need to put in 1. So we have velocity before impact and velocity after impact. So usually we don't know that. Fortunately, velocity 0 also counts as an input value. And that's usually the case. One is standing, the other one is hitting it. So we can just leave that as it is, and we can press on calculate. What happens now is we get the ES values, we get the final distance, we get the stiffness of the other car, we'll get the pre-impact velocity, run-out velocity, change of velocity, and so on. We get velocity difference before collision, we get the K value, impact duration, how long the compression phase is, and the missing braking distance. So if the Skoda would have continued just braking, it would have needed 3.4 meters to further brake. Also, we have it here in our depiction with our cars going in. And yeah, so, but that's not all of it. So what we could do now is we can double check that with our values in the PDF. So let's check. So what they measured is 26 kilometers per hour. What we got is 25 kilometers per hour. So slight changes in these three values would lead us to that. So that's pretty good. They got impact time of 96 milliseconds. We have 81, so we would need to make it a little bit stiffer. What else? They got an NES value 9.3 and 14.5. We got 9.5 and 13.7, so like also very close. So that's quite decently. Of course, we've just done now this in a quick and dirty way, but yeah, I think the results are pretty good for that. But this module can do a little bit more. It can also deal with passenger stress. Oh, okay, now it says me mass of the occupants shouldn't be 0, so I need to put in like a person on the driver's seat. Let's say 80 kilos here. Okay. So what we have here is now a calculation that puts in the the relative accelerations that people get depending on the stiffness of the driver's seat they are sitting in. So when I click on calculate, with all these values of the cushion and so on, all the values of the chair, we get as a result, well, for the vehicular acceleration and the passenger acceleration, we get the same mean value, but we get a different maximum value. Why is that the case? Because when the car gets hit, the first thing that happens is that the passenger gets pressed into its seat, and the seat kind of acts as a spring. So it will like first slow down the acceleration of the person, but then it will like jump forward and accelerate the passenger even more. And this usually generates a movement between the body of the person and the head of the person. And that's what causes, at least to my knowledge, the Whip-lash syndrome. I'm of course not a medical doctor, but that's how I understood it. So it's very important to point out that there is a difference between maximum vehicular acceleration and maximum passenger acceleration. Okay, that was it for today. I hope you enjoyed the video and have a lovely day. Bye bye.